Hey everybody, your Friendly Math Tutor here with video 3 of our SAT one-sheet breakdown series. So the PDF files of both the one-sheet and the examples that we'll do in this video are linked below. Please subscribe, check out our Instagram, Facebook, and TikTok for more videos related to SAT and even other topics like BC, AB Calculus. So I think it's time to dive into today's part of the one sheet. All right, let's dive into the one sheet for today. So we are going to look at, for today, we are going to look at common problem types. And in video 2, we looked at the first 3. So here in video 3, we're going to look at percents, general graphing, and statistics. So let's dive into percents. So when we take a look at percents, we've got some categories here where we're looking at percent decrease and percent increase and percent change, which really percent change, we're kind of going to lump into both of these. So let's first take a look at percent decrease. So the key to a lot of percentage problems on the SAT comes down to this concept of if you have a 25% discount, you don't want to think of it, so we know 25% is 0.25 as a decimal. We don't really want to think about doing that because then that's finding the discount, and we typically want to know what the final price is. So what we're going to do is think of it as a 25% discount is like paying 75% of the price. So therefore, we're going to multiply by 0.75 for a 25% discount. So let's take a look at how we can use that in example 1. So due to deforestation, researchers expect the deer population to decline by 6% every year. If the current deer population is 12,000, what is the approximate expected population size 10 years from now? So this is also an exponential problem, but where the percent comes in is if there's a decline of 6%, then that means the deer are keeping 94% of their population. So I really want to be multiplying by 0.94. And if we start with 12,000, there's 12,000 deer, and each year we're going to keep 94% of the deer. That is a 6% decline. And if we do that year after year after year, this is where repeated multiplication becomes exponentials. So we're going to raise it to the 10th power to see how many deer there was 10 years from now. So I'm just going to type that into my calculator, and that gives us about 6,464. So the closest answer here is B. All right, so the key to the problem is multiplying over and over by 0.94, which is really a 6% decrease. Now let's look at another decrease problem. Here we kind of work the other way. So this year a company consumed 30% fewer sheets of paper than it did last year. If the company used 270,000 this year, approximately how many sheets did it use last year? So 30% less than last year, or 30% fewer, is really 70% of it. All right, so 30% fewer means they kept 70% of the sheets. So that's 0.7. So 30% fewer really is represented by 0.7. And if you want to do 0.70, just so you can see the 70, that might be helpful. And so we kept 70% of what we did last year, which we don't know in this problem. So that's X, and that should equal 270,000. So that means to solve this problem, we just have to divide each side by 0.70. So we're really taking 270,000 divided by 0.7, and that is about 386,000. Again, you can check that in the calculator. But again, the key to the problem is knowing that if it's 30% fewer, then we're multiplying by 0.7. Okay, that's again, a really key concept on the SAT when it comes to percent problems. All right, let's keep it moving. So now we're going to look at percent increase. So now if we do something such as a sales tax, so a 7% sales tax would mean 7% is 0.07. But if we're increasing it, instead of multiplying by 0.07 and adding it back, if we just multiply by 1.07, then that's the same thing. That's a way we can do it as a single step. So it's just like before, we're taking the percentage and taking it away from 100. Now we're taking a percentage and adding it to 100. And the key is to be able to use it as a single decimal. So Juan starts with $200. The value of the antique is estimated to increase 10% over its value the previous year. So we're increasing by 10%. So that means we're multiplying by 1.10. The estimated value of the antique 2 years after the purchase can be represented by 200A, where A is a constant. So if you think about it, we start with 200. It's kind of like the deer problem. We multiply by this decimal, and then we are doing that for 2 years. So we're raising it to the second power, and they want to know 200 times A. So A really represents whatever 1.1 squared is, or 1.1 times 1.1. I should just know that, but I used a calculator. So we should know that 11 squared is 121, so 1.1 squared is 1.21. So 1.21 is what we would multiply 200 by in this case. All right, so again, 10% increase means we multiply by 1.10. Now let's take a look at our last percent increase problem, or our last percent problem overall. So this kind of combines both techniques. So first we lose 18%. So losing 18% means we keep 82%. So that's 0.82. On the second turn, she increases by 36%. So increasing by 36% means 1.36. All right, so that pretty much eliminates A and B. And we're down to a problem that has to have 0.82 and 1.36 in it. Now this is pretty important. Her final card count after these two turns is N. Which of the following represents her starting count in terms of N? Well, this is what we're multiplying her starting value by, which we don't know. And in the end, after doing these percent increase and decrease, we end up with N. So this is why it's not D. It seems like it should be D. But they're actually asking us the original, which means the original we work backwards by dividing. So you should be able to see that it's C, because we're going to have to divide each side by 0.82 times 1.36. Whoops. So the first part of this problem is just recognizing that we are using 0.82 and 1.36. That'll at least get us down to C and D. Then we have to realize that if they gave us if we needed it in terms of the initial amount, then we would have been multiplying. But since we were given the final amount and we had to work backwards to find the initial amount, we're dividing by the decimals. All right. So that wraps up our percents. Now let's move on to the next category here in common problem types, and let's take a look at some general graphing. So general graphing here, we've got kind of four main problems, and we'll take a look first at basic transformations. So these are some, there are more than this, but these are the ones that I think show up the most on the SAT, especially the left column I think is the most common. So we have left and right shifts. So x minus h is a right shift h, x plus h is a left shift h. Anything that's attached to x moves it horizontally. And then if we're adding and subtracting things outside of the function, that affects it in the y direction, so that's up or down. Then we've got our vertical stretch when we multiply. Then we've got our reflection whenever we multiply by something that's negative. So let's see how we can kind of put that into action. So here we have a function that's f of x plus 6. And that is plus 6. If we look over here, that is a shift up 6 units. So f of x is given here. G of x is this function shifted up 6 units. And it wants to know the maximum value. So if the maximum value of this function occurs at any one of these places, which is a value of 2, if we were to move that up 6 units, then it's going to move up this way, and it's going to go from 2 plus 6 to 8. So the maximum value is going to be 8. So the key to that problem is just knowing that this is a transformation that shifts it up 6 units. All right. On to the next problem. So now we're going to look at finding intercepts. So intercepts are really, really simple. If they ever ask you for an x or a y intercept, x intercepts you always substitute 0 for y intercepts you always substitute 0 for x. I guess the exception is when you have a y equals mx plus b, you just know that b is the y-intercept, but at the same time, if you were to plug in 0 for x, you would still get the same answer. So this one says, how many x-intercepts does the graph have? Well, x-intercepts means we substitute 0 for y. F of x is y, so we're really doing this. And there ends up being 3 of them, so 0, 4, and 5. Now 4 has a multiplicity of 2, but it's still a single x-intercept. And 5 has a multiplicity of 3, but again, it's still physically, when you look at the graph, only crosses the x-axis at that one value. So there ends up being 3 x-intercepts, even though some of the x-intercepts have higher multiplicities. All right. Now let's keep going, and we're going to take a look at some of the quick tips. So the first quick tip is, when given a specific coordinate pair in a problem, just plug it into the given equation to get started. So for instance, if we take a look at this problem, it seems to be, they give us a graph, they give us an equation, there's kind of a lot going on. But what I would do, just to get you started, look at this. They give me a coordinate, I'm just going to plug it in. So a becomes y, and x becomes -10. So if I solve this, -10 plus 4 is -6. -6 squared is 36. 36 times 1/4 is 9, and 9 minus 5 is 4. So that means a is 4. Now they want a comma b. Well, a comma b, I'll go over here, is really 4 comma b. Well, now I have another point, so I'm going to plug that in. So b equals 1/4 times 4 plus 4 minus 5. Whoops, squared. So b equals 4 plus 4 is 16. 16 squared, or sorry, 4 plus 4 is not 16. 4 plus 4 is 8. 8 squared is 64. 64 divided by 4 is 16. And 16 minus 5 is 11. They want to know the value of b, so b is 11. All right, so sometimes these problems, you can't see the end from the beginning, and that's okay. You just have to have things to get started. So when, there's certain things that we just know to do to get started. Here's another thing you can do. If you have a coordinate pair that's given in the problem, most of the time, plugging that in is a way to get started. And then as you go, the problem will become more clear as to kind of where we're heading. So let's look at another tip that has to do with graphs in general. When matching a graph or table to possible equations, substitute points from the table into the equation to eliminate 3 of the answers. So here we go. Here we got a problem where one way you could look at this is if you know your equation types or your function types. So this curves like an exponential. It's not quadratic and it's not linear. But unfortunately, all of our answers are exponential, so that doesn't help eliminate any answers. So then what I would do is I would test out some points. So maybe just start here. We know this is scaled by 2's, so this is the point 1, 8. So I'm just going to throw that in. So I'm kind of checking my answers, a strategy that we went over in video 1. But I also need to eliminate answers because it's possible that 1, 8 could work for 2 of these. It could work for the wrong answer, and then I'll have to pick another point. But let's see where it goes. So for A, 3 to the first is 3. That's not 8, so that's wrong. 3 to the first is... actually, I just realized I made a mistake. So let's fix that. I hope everybody watching this caught that and was telling me to stop, because I heard you. That's 6, not 8. So that's my bad. So still, 3 to the first is not 6. I thought it was this one, but it's not. Okay, so now we're back on track. 3 to the first is 3. 3 times 2 is 6. So I'm not going to say that's my answer. I'm going to just not eliminate it. Plug in 1 here. 2 to the first is 2, not 6. Now this is what happens. 2 to the first is 2. 2 times 3 is 6. So 2 of them give me 6. So then maybe I'll go here. I could have done this in the beginning. This is 0, 2. So I only need to check the answers that are left. So 3 to the 0 is 1. 1 times 2 is 2. 2 to the 0 is 1. 1 times 3 is 3. So the answer is B. And I guess I would have gotten that had I just chosen 0, 2 at first. If you did that, then great. I chose this point first, and I kind of wanted to show you what would happen when there were 2 that were left to kind of illustrate this point. So again, if this was a table or a graph, one way to figure out what the equation is to simply just plug points in. I could have done this point too, 2, 18. They're really the 3 points that I had choices of. All right. So that is the end of our general graphing tips. Let's head back to our last common problem type and the last part of this video on statistics. So let's take a look at our first statistics kind of part here. The mean lowers when a high value is removed and is raised when a lower value is eliminated. And then the median is affected minimally, if at all, when high and low values are eliminated. All right, so that's just kind of a basic understanding of how mean and median can be affected. So they like to ask a lot of questions or surrounding these concepts. So if the dot plot's representing the 2 soft drinks with the lowest sugar content are removed from the dot plot, what will happen to the mean, median, and range of the new data set? Okay, so if we eliminate low values, the mean has to go up. Has to go up. So the mean will increase, the mean will increase, the mean will increase. Okay, so that doesn't help because every answer says the mean will increase. Now the median says it'll be minimally, if at all, affected. Well, we still, in this case, have to kind of figure that out. So if we have 11, then the sixth value, so if you do 11 divided by 2 is 5.5 and round up to 6, the sixth value will be the median. So the median before is 1, 2, 3, 4, 5, 6 is 25. And the median after, if we get rid of 2, there's now 9. So 9 divided by 2 is 4.5 and round up to 5. So the fifth value will be the median. So it'll be 1, 2, 3, 4, 5. So now it jumps to 30. So now the median is bigger. So the mean and median will increase. So only the mean and range will not just, definitely the median has to be part of it. So now it comes down to the range. Well, the range is, I didn't put that over here, but the range is something that you should know is the highest minus the lowest. So the highest is minus the lowest. Well, what's going to end up happening is the original range is 30, but then the range becomes 10. So the range is actually going to go down by getting rid of low values. So that will not increase. So the answer is C. Only the mean and median will increase. All right. So we know the mean will increase without actually finding the mean. That's kind of the shortcut in this problem. The median will be minimally, if at all, which means we have to check that one. The range is also pretty easy. When you get rid of a low value, the range is going to go down. Or if you get rid of a high value, the range will just go down because you'll literally be shrinking the range. Okay. So let's take a look at our next type of problem. And this one has to do with standard deviation. So standard deviation tends to be higher when there are more extreme values. All right. So if we take a look at this just wants to describe the standard deviation between the two sets. So if you just look at the sets, notice all the numbers are the same. So that's why I said tends to be high, tends to be higher. That'll definitely be true of all of the numbers on the bottom of these dot plots are the same. So just notice that this data set S has more extreme values, so it's going to have a higher standard deviation. So they don't have the same. The standard deviation of R is greater. That's not true. R is less than that one, so that's it. And this one just doesn't even make any sense. So since dataset S has more extreme values than dataset R has a lower standard deviation. All right, so that's really what you have to understand about standard deviation. Standard deviation is a measure of spread, so the data is less spread out in dataset R because there's less values that are far away from the middle. All right, moving on. Let's take a look at a couple problems related to the median of a frequency table. So let me just illustrate how to do this. So we've got this histogram. We can probably skim through this and just say it just wants to know in which interval will the median price be. All right. So there's 27 books. So what I would do is 27 divided by 2. 27 divided by 2 is 13.5. We are going to add up the frequencies until we get the first bar that brings us over 13.5. So the first frequency is 9. Well, 9's not bigger than 13.5, so that interval will not contain the median. Then I add the next interval, which is 11. The frequency is 11. Well, this is 20, which puts me over 13.5. So the median must lie in that interval, so somewhere between 5 and 10, so at least 5, but less than 10. So that's how we can find the median without having to do the whole cross-out method, which we would do if there was just like 5 or 6. If there wasn't a lot of values, we could do the cross-out method. But here we can't really do it because we don't know what the specific values are. So this is one way to do it with a frequency table or histogram. And let's take a look at another example. Actually, my bad. So then we have one more example. I was thinking we were doing an example of median again, but we're not. We are doing an example of margin of error. So what margin of error is in statistics, when you do a sample, you're trying to do a sample of a smaller group and trying to project that to a larger population. And usually you're trying to find something like the mean. And what ends up happening is you can't actually find the mean of the population because it's not feasible. There's just too many, there's just too many data points or people. But we use the sample median to estimate what it would be. And then what ends up happening is if we choose a larger, we have this thing called margin of error, and that's how far off we think our estimate is from the actual unknown value. And the larger we make the sample size, the smaller the margin of error. I mean, imagine you ask just like 6 people in your sample something, that wouldn't be very reliable because it's only 6 people. And if you're trying to project that to millions of people in a population, that's not going to be very, that margin of error is going to be very large. But if you ask 500 people, well, now the results you get would give you a smaller margin of error because you have more data that supports whatever you're trying to find out. So this one just says if the biologist wants an estimate that has a smaller margin of error associated with it, that can be generalized to the entire population. So if we just look at this using a different tool to measure butterflies, well, we wouldn't know that. We're not expected to know about tools that measure butterflies. Measuring butterflies at 2 different times of the day, I don't think that has much to do with it. Selecting and measuring only the butterflies that look the smallest, that doesn't really sound like a random sample. Selecting and measuring a larger random sample. So again, the larger the sample size, the smaller the margin of error. That is the key takeaway from this problem. All right, let's head back. And that is the end of common problem types. So today we learned about percentages and how to use those to represent decimals, thinking of percent decrease and percent increase as a single decimal value. We went over some general graphing tips, some transformations, intercepts, and other quick tips to do problems, certain problems, and then statistics having to do with mean and median and standard deviation, as well as just a margin of error relating to sample sizes. All right. Okay, I hope that was helpful. Check out the other videos in the series for all the rest of the one sheet and all the other examples that I go over. Make sure you subscribe. Check out our TikTok, Instagram, and Facebook, where we've got a bunch of other videos surrounding SAT and even subjects like ABBC calculus. All right, hope that was helpful, and take care.